Everyone, what's up? Welcome to the class. Good evening, everyone. If I'm audible and visible, please write you in the chat box. You know the drill. Yes. और बताओ क्या हाल चाल सब बढ़िया. So welcome to this fourth episode of the series Mirror on the Wall. And in the previous week, I would like to remind you that we have covered all the basics of this particular chapter. In optical isomerism, we understood what optical activity means for chemical compounds. We understood what chirality means. We understood how to make Fisher projections. We understood how to write configurations of R and S for Fisher projections and other wedge dash structures. And what we will do today and in the next class is that we will build upon those basic concepts. In the previous class, we had also talked about symmetry elements. Yes, so I hope you have revised the previous 3 classes properly, because today we are going to take those concepts and apply them even further. So we are going to use the ideas of optical activity, RS configuration, plane of symmetry, center of symmetry, axis of symmetry, etc. to do some questions. Then I'll give you a few fun days. In the next class, that is going to be day after tomorrow, that is on Wednesday, we will also discuss those advanced level topics where, they say chirality without a chiral center, olenes, etc., some biphenyl compounds, those have optical activity even though there is no chiral center in them. So, such questions will also become a topic of our discussion, and as I promised to you, we will take it from the basic level to the advanced level. Sanjay Krishna is saying the thumbnail is dope. Thank you so much, man. चलो तो आज का क्लास शुरू करते हैं. A little bit about myself. If you are new over here, my name is Pahul and I have lots of hobbies. I like to travel. On my motorcycle, which I'm not doing since a very long time because of the lockdown. Frustrating. Like to cook food. I'm sort of a musician. I like to beatbox, etc. And I love to just pass my time and do nothing. Also had a pinch of grammar Nazi. So yeah, I'm an alumnus of IIT Bombay. If you're new to the channel, welcome to Catalysis. If you're old, then awesome. Chalo ji. So now for the first 15 to 20 minutes, we are going to do a lot of questions. Rapid fire hone wala hai. So my dear friends, let's do these questions. So the first question over here is this particular Fisher projection. What you have to tell me, number 1, is this optically active? Very simple question, is this optically active? And number 2, you have to write the configurations. Okay, RS configuration dena hai in molecule ko. Alright, Tanuj, that is a Ducati Diavel. Okay, yep. No, that's not an intruder, that's a Ducati Diavel yaar. Chalo ji, batao. Is this optically active? See, what you can do in order to check whether this is optically active or not is a lot of things. You can draw a Fisher projection, you can draw a wedge dash projection, and then you can, try to see whether that is optically active or not by taking the mirror image. Or you could simply fish for some symmetry elements. Look at this compound. This is a chiral center, we understand. This is also a chiral center, we understand, because on both of these carbons, all the 4 groups that are attached are different. Okay, great. Now, is there a plane of symmetry? I will write over here, there is no plane of symmetry. No matter how hard you try in this molecule, there is no plane of symmetry whatsoever. Yes, plane of symmetry तो नहीं है. Okay, interesting. और क्या देख सकते हैं? Is there a center of symmetry? Definitely not. Is there an axis of symmetry? Only a C1 axis, that is 360 degree rotation. Pretty much no symmetry over here, yes? Okay. So, as I am looking at your answers in the chat box, very well done. Yes, this is optically active. Good. Awesome. High five. Now, let's talk about the configurations of these 2 carbon atoms. So, the top one, first priority goes to chlorine, second priority goes to oxygen, obviously. Then you have to compare this carbon with this carbon. Interesting. Let's call this C1, let's call this one C2. For now, let's call it C1 and C2. Okay. तो अब क्या करेंगे अपन? Let's try to figure out. This is the red carbon. On that you have a C1 and another C2. On C1 you have a double bond O and single bond OH. On C2 you have a fluorine you have an NO2 and you have another hydrogen. Now, my dear friends, even if you were to break this oxygen into two different oxygens, one real, one fake, according to CIP rules that we did in the previous week, you would realize that this oxygen gets, this fluorine gets the most priority because fluorine's atomic number is higher than oxygen and nitrogen. So this is the place where you could have done a silly mistake. Yes, the third priority goes to C2 over here. ठीक है, तो third priority कहाँ चली जाएगी? इधर, and this will be your fourth priority. Is that fine? Understood? CIP rules are being applied over here very well. Fine. So oxygen versus fluorine, obviously fluorine will win because its atomic number is higher. Now, this being the least priority group, it's already at the back. Least priority group already at the back. So you just have to move from 1 to 2 to 3. So the top carbon becomes S. Fine. Absolutely awesome. Now looking at the bottom carbon, similar things will happen over here. This is the first priority. This is the second priority. This is the third priority. Very easy because hydrogen is already the fourth priority. Now hydrogen is towards you. So whatever order you get, this is the wrong order. So what is right for this particular carbon? Right once again is S. ठीक है? Awesome. Vanshika, if you are new to our channel, welcome. If you haven't watched the previous classes of this particular chapter, please make sure you do so after the telecast of this live session is over. Alright. So my dear friends, we have discussed in the episode 2 of Mirror Mirror on the Wall how to give RS configuration. Saksham, we'll see man. We'll try if possible. ठीक है? Okay. Kavita, I'll talk about that separately some other day. Okay? ठीक है? चलो जी. So, agreed, both are S. मान लिया, कोई गलती दिखती है तो बता दो. If you think there's something wrong, then tell me. But in my opinion, both of these are S, and yes, this is an optically active structure. Now, moving on. This particular structure, is this optically active or not? Is this optically active? फटाफट से बताने का. Is this optically active? My dear friends, to solve such structures of cyclohexane, there is an easier way to do it. What you have to do is you make such kind of a projection. Okay? ये वाला projection बनाने का, these are known as Haworth projections. Okay, if you remember the chapter of conformers, you might remember Haworth projections. If you don't, then we will do a beautiful revision session on conformers. If you want to study conformers from the beginning, then you can definitely go and watch Epic GOC. Okay, तो इस पे आते हैं. Now in the Haworth projection, do you notice that the OH is pointing upwards? Okay, let's make the OH pointing upwards. Then on the next carbon, the COOH is also pointing upwards. Do you realize that there will be an axial hydrogen over here and there is an equatorial COOH? Remember conformations of cyclohexane. If you don't remember this, Epic GOC after the class, and then we'll do a revision class for conformers as well, don't worry. But these are generally topics from 11th class. They are also in the NCRT. So I'm assuming that since you are in 12th class, majority of you already know what conformers are. Cool. So COOH is also pointing towards the top. अब बताओ, is this optically active or not? Saksham, thank you. Kamal is saying that yes, it is optically active. Lone is saying it has two chiral centers. Okay. Agreed with both of you. Shagun is saying it is optically active. Lone. What kind of a name is that? Kundan is here to sing songs and dance. Kundan, sort your priorities in life, bro. ठीक है. Dilip, I might have missed your chat, sorry. चलो जी, तो Rakesh is saying it is optically active. Okay, Shirish is saying it is not optically active. The best way to think about the optical activity of this compound, okay, इसकी optical activity अगर सोचनी है, moving the page a little bit, ठीक है. All you need to do is draw its mirror image. Do one thing. If you are smart enough, you will be able to understand that this does not have any plane of symmetry or center of symmetry, try to draw its mirror image. एक बार बना के देख लो and satisfy yourself. Okay, what will happen in the mirror images? I'm drawing a smaller one because there's not enough space on this page. ठीक है जी, तो यहाँ ऊपर आएगा OH, यहाँ आएगा COOH. Fine. Now try to overlap these two. If you rotate the mirror image that you've drawn and try to overlap, you will realize that the COOH starts overlapping with the OH, and you will realize that the OH starts overlapping with the COOH. So my dear friends, this is definitely optically active. Fine. So you could have thought about plane of symmetry, center of symmetry. As you realize, this does not have any plane of symmetry. This does not have any center of symmetry. Pretty obvious. कहीं से भी line नहीं खींच सकते that divides this compound into two equal halves. Okay. So no symmetric elements, hence it is optically active. Very beautiful. Let's go to the next question. Once again, Fisher projections. फटाफट से करेंगे इसको. Optically active. Very simple. Yes, it is optically active. You have two chiral centers and it's a very asymmetric molecule. You can't find any element of symmetry. Fatafat say, tell me about the configurations. What about the configuration of the red carbon? This is the first priority. You have to worry about the second priority. So for the second priority, let's call this green carbon C1 and this black carbon C2. Alright. So अब C1 C2 में compare करते हैं. This is a question where you need to think about priorities. C1 has double bond O, single bond OH. C2 has a chlorine, a CH3 and a hydrogen. So my dear friends, do you realize that chlorine wins? Yes, chlorine wins. So this guy gets second priority, this guy gets third priority. Now hydrogen is towards you. This looks like R, but since hydrogen is towards you, this will be S. The first one is S. Very nice. What about the second one now? Second one को क्या करेंगे? Chlorine gets the first priority. Then, where's the second priority? ये वाला carbon या ये वाला carbon? The bottom carbon has only hydrogens. The red carbon has oxygens on it. So my dear friends, do you realize that the top carbon will get the second priority and the bottom gets the third priority? Hydrogen is towards you, look like S. So it should be R. So the configuration over here is S and R. You can verify if you think there is something wrong. Tell me. Om Jena is saying, does it mean it's non-superimposable mirror image? Yes, Om, absolutely correct. Optical active means that its mirror image cannot superimpose with the original compound. Okay, very, very simple. SR configuration. Now we are gaining some speed. So in case you've joined this class for the very first time in life, make sure after this live telecast, you go back to the playlist of this channel and watch the entire series of Mirror Mirror on the Wall. Fine. चलो जी आगे बढ़ते हैं. Is this optically active? Is this optically active? Is this optically active? This is a good question. Saksham, it is not my birthday. My dear friends, I'll tell you everyone once and for all, my birthday is on the 1st of April. Today is not my birthday. Okay. Every single day someone wishes me happy birthday in the chat box. Why? I have no idea why. So as answers have started pouring in, Rakesh and Ramesh and Kartike and DDR4X Corsair. Why is a graphics card in the chat box, man? Kuldeep, Anurag, Bathinde Ala. Okay, everyone is giving me the correct answer. This is not optically active. Very beautiful, people. Why is it not optically active? Because I am pretty sure you can see that there is a plane of symmetry. Divide this molecule into half right from the middle. है ना जी? ठीक है? Can you do that? बिल्कुल बीच में से इसको तोड़ दो आधा. Yeah, I'll try to draw a 3D image of the plane of symmetry. I might be really bad at it, but yeah, let's try. ठीक है? I'm just trying to do some really interesting things. Okay, So plane of symmetry में do you realize this is the plane of symmetry? बात चमक रही है. If you cut this structure right into half, जहाँ पे वो सर्कल है ना, this point that I've made over here, that is where the plane of symmetry is passing through. So yes, there is a plane of symmetry over here. POS बोलो तो plane of symmetry. Since there is a plane of symmetry, this is optically inactive. This entire molecule is achiral. But do you realize that this molecule has two chiral centers? Two chiral centers. But overall, symmetric, I can write that. Why two chiral centers? Notice this carbon and this carbon. There are two optically active centers, but overall this molecule is symmetric in nature. Since overall it is symmetric, it means that it is achiral, it is not optically active, and such compounds which have multiple chiral centers, but because of overall symmetry, they are achiral, such compounds are known as mesocompounds. Okay, what is a mesocompound? Mesocompound is a compound where you have chiral centers, but because of overall symmetry, the overall molecule is achiral in nature. Okay, so this is a mesocompound. And NS logs, please refresh, there is no buffering. ठीक है जी, mesocompound. Lonol, okay man, no problem, you can watch it later. This is a mesocompound. My suggestion to you is try to make its Fisher projection as well. इसका एक Fisher projection बना के कोशिश करना. Try to make its Fisher projection and see what's going on. Okay? Fine. If you want to make its Fisher projection, this is what it will look like. I have already told you guys how to make Fisher projections earlier, so please make sure you revise all the classes. Okay? How do you make the Fisher projection? You are looking at it from the bottom. नीचे से देखोगे, so chlorine and hydrogen will be coming towards you and bromine will be going away from you. That's exactly what happens in a Fisher projection. And you can see over here very beautifully that there is a plane of symmetry. Okay? Marshmallow is asking, does optical activity mean that the compound can rotate people? What? Gajendra, no. Mesocompounds are optically inactive, bro. They are not optically active. ये वाला बताओ, is this optically active? ये हो गया और interesting हो गया थोड़ा. This has become even more interesting now. Jeets, these are advanced questions, man. And in the next class, there will be even more advanced questions. So don't worry. Mehboob is asking, sir, does an asymmetrical resonating structure have plane of symmetry? Depends on the resonating structure, man. Because you don't think about individual resonating structures ever, you think about the final hybrid. That is what matters. Okay. Is this optically active? Interesting, right? Do one thing. Let's do it from the very basic idea of trying to make a mirror image. Let's do the mirror on the wall. Okay. So if I have to make its mirror image, it's going to look something like this. Okay. Let's just mark the atoms as well. So you're going to have chlorine over here, hydrogen over here, the hydrogen over here, chlorine over here, and there will be a bromine on the top. Fine. This is the mirror image. Now, try to overlap these two structures with each other. Just try to overlap. You will see that the chlorines don't overlap with chlorines, the hydrogens don't overlap with the hydrogens. This is not overlapping with the original structure. So I will write over here that this is non-superimposable. In your mind, try to rotate the mirror image as much as you want. Okay, don't break any bond. Try to rotate it as much as you want and try to overlap it with the initial. It will not overlap no matter how hard you try. Okay, these two are non-superimposable with each other. Hence, yes, it is optically active. This is optically active. Over here, there is no plane of symmetry. There is no center of symmetry. Now, some of you will say, sir, yeah, some of you will say that, sir, why don't you draw us a Fisher projection of this guy? Okay, let's draw it. Fisher projection kaise banani hai? Look at it from the bottom. When you look at it from the bottom, just lie down on the floor and look at it from the bottom. Chlorine and hydrogen coming towards you, hydrogen, chlorine coming towards you, bromines going away from you. Yes. So, let us call this carbon number 1, let's call this carbon number 2. Notice the Fisher projection I am drawing very carefully, okay? बिल्कुल इसको नीचे लेट के देखना as if you're repairing a car. So, bromines will go on the top and bottom. This is my C1 and this is my C2, okay? Understand the kind of Fisher projection that I'm drawing. I'm looking at it right from the bottom, okay? तो मैं कैसे लेटा हूँ इसको देखने के लिए? This is me. I'll draw that in blue color. These are my hands, this is my head, these are my eyes, this is my... Do you understand now how I am looking at this structure? If I look at this structure from that perspective, do you realize this is the Fisher projection I will get? Chamak gaya? Okay, fine. Now, my dear friends, you would say that, sir, if we rotate it by 180 degrees, I will get the same structure. Yeah. If I rotate this compound by 180 degrees, I will get the same structure, isn't it? देखो Fisher projection में. हाँ, बात तो सही है ना? So, my dear friends, if I rotate it by 180 degrees, in 360 degree rotations, I am getting two similar structures. This implies that this has a C2 axis of symmetry. Dikha C2 axis. If you don't know what axis of symmetry are, then please go back and watch the previous class. We have discussed a lot about the C2 axis of symmetry. Okay. So, C2 axis of symmetry, because in one 360 degree rotation, you are getting two similar structures. Okay, great. But this compound is still optically active. Yes. So, my dear friends, this is something that you have to remember, okay? Axis of symmetry, okay, axis of symmetry tells us nothing about optical activity. Okay, axis of symmetry tells us nothing about optically active compounds. Plane of symmetry and center of symmetry are important. If you have a plane of symmetry, if you have a center of symmetry, compound will be optically inactive. Axis of symmetry jitni marji dhoond lo. Okay, axis of symmetry tells us nothing about optical activity. Please take care of this idea. Okay, so this is an optically active compound. It does have a C2 axis of symmetry, but still it is optically active. In case you want to write the configurations of the of the Fisher projection, you are most welcome to do so. Anyway, let's move on to the next question, which is something that we've already discussed in a previous class. Do you realize that this molecule that I've drawn over here has a very beautiful plane of symmetry right in the middle? Yeah, has a plane of symmetry. So this guy is optically inactive. Okay, very nice. But now let me ask you about this guy. Instead of both CH3s being on the same side, what about these CH3 being on the opposite side? Now it becomes interesting. This has become a much better question now. Yeah, cool. So as I told you that for cyclohexane kind of structures, the best way to go around it is by drawing Haworth projections. How do I draw its Haworth projection? Okay? And people, I am deliberately going fast today because we've covered the basics at a very slow pace in the previous week. So from now on, a little more speed. Alright? So अब क्या होगा यहाँ पे? One CH3 is at the bottom, one CH3 is at the top. यही है ना structure. This is the exact structure that is given. If this is carbon 1, this is carbon 2, this is my carbon 1, this is my carbon 2. Okay, fine. I can draw this particular structure. Great. Now tell me whether this is optically active or not. A lot of people are saying it is optically active. Shantanu is saying optically active, but Hindiala is saying, sir, aap bahut acha padhate. Thank you, bro. And Pallavi is saying it is optically active. Sakhlain Afroz, एक बार structure दोबारा से देखो भाई. Hanish, this is an advanced level concept, bro. Please focus more attention towards the class and less towards the chat box, because वहाँ पे कोई advanced level नहीं हो रहा, यही हो रहा है. Okay. So, my dear friends, what I invite you to do is make its mirror image. Okay, let us do that. If I do make its mirror image, I would realize something very, very, very interesting. Okay, this is the mirror image. Let me draw them in black color just for aesthetic consistency. Okay, try to overlap each of these. As it is, they don't overlap. If you rotate this guy like this, still they won't overlap. है ना जी? If you rotate this guy, ऐसा है अभी, if you rotate it like this, this will come towards the bottom, this will go towards the top. You still won't be able to superimpose the mirror image on the initial. Once again, thinking about symmetry elements, there is no plane of symmetry. You can't cut it in the middle and say it's symmetric. No. Can you see over here? It's not symmetric on both sides because one of the CH3s is pointing upwards, one of the CH3s is pointing downwards. There is no plane of symmetry. Neither is there a center of symmetry. That is pretty obvious to see over here. No symmetry element. Mirror image does not superimpose. My dear friends, this particular structure over here is optically active. And at the bottom are the two mirror images that are optically active for this structure. So do you realize just by changing the orientation of CH3s, sorry, my mic fell off. Hold on. So do you realize just by changing the orientation of the CH3s, a compound can become optically active and optically inactive? So do you realize that the chemical properties of these compounds will be different from each other? Which compounds? Let me tell you. Let me draw these for you so that it's easier for us to understand. Let's first draw these three hexagons quickly. Okay. One of them is where both the CH3s are on the same side. Do you realize that these three compounds will have different chemical properties? Yes. My dear friends, it's a very interesting case of 1,2-dimethyl cyclohexane. The first one is cis 1,2-dimethyl cyclohexane. Yes, cis 1,2 dimethyl cyclohexane. This is an advanced level idea. A lot of people tell this incorrectly. I've seen some people doing this incorrectly online. गलती से हो जाता है. So cis, and then the rest of them are trans. Yes. But both of these are mirror images of each other. Very fancy, very interesting. Good question. I've taken this in Epic GOC as well. In case you watched that, you would remember. Next question is also something that we have solved in Epic GOC, but is supremely relevant to this particular class as well. A compound in front of you, wedge dash structures are given. Yeah. You need to figure out what the correct statements are. बताइए. Kundan, I agree with you. Tanveer, thank you so much. Lakhori Lome is saying, sir, please do a video on physics as well. I don't know physics properly, brother. Shyam Deshmukh is asking your qualifications. Bro, I have come from Mars. On Mars, everyone is a scientist. Shyam, I am an alumnus of IIT Bombay. I have completed my 5-year integrated MSc in chemistry from IIT Bombay. I graduated in 2016. I hope these are qualifications enough. Shaikh, thank you so much, yaar. Batao. Correct statements. By the way, this is a multiple correct. Okay, this is a multiple correct question. ध्यान से देखो, द वे द स्ट्रक्चर इज ड्रॉन इज द मोस्ट कंफ्यूजिंग थिंग एवर. ओके, द वे द स्ट्रक्चर इज ड्रॉन इज अ लिटिल कंफ्यूजिंग. पहले तो स्ट्रक्चर को सिंप्लीफाई करके लिखो, मेक द स्ट्रक्चर अ लिटिल सिंपल एंड देन ट्राई टू फिगर आउट व्हाट्स गोइंग ऑन. ओके, सिंप्लीफाई करें स्ट्रक्चर को थोड़ा, इंस्टेड ऑफ दीज वेजेस एंड डैशेस दैट आर utterly confusing. Let's just do something like this. Yeah, I can do that. And now let's just mark the atoms. Direction change कोई भी नहीं है, just made better figurines of whatever is already given. Fine. बात बनी? ठीक. Now the structure that I have given to you on the right hand side, the sawhorse projection, now try to work with that. Now try to work with that. All you need to do is just rotate this by 60 degrees. Okay, जो front carbon है ना, just rotate it by 60 degrees. What will you get if I rotate it by 60 degrees? Let me draw it for you. Let's make the structure even better. Okay, so there is going to be a chlorine at the top, CH3 at the right and H at the left. So फटाफट से बनाएंगे CH3 and H. Now my dear friends, look at this particular question and look at किथे गया this question. Do you realize, sorry, this one, do you realize they are the same questions? This question and this question are absolutely same. We just did this, we just deduced that it is optically active. Aren't they absolutely similar to each other? Yes. So my dear friends, I hope you realize if I draw the Fisher projection of this guy, it's going to look something like this. How will I draw the Fisher projection? Let me draw that stick figure person. I am going to look at the Fisher projection in this perspective. Okay. वैसे नीचे लेट के देखेगा इसको. Fine. Okay. So if I am looking at this structure from that perspective, my chlorines will obviously go like this. This is the CH3, this is the hydrogen, this is the hydrogen, this is the CH3. And now you would notice that right in the middle, there is a 180 degree axis of symmetry. If I rotate the molecule 180 degrees, you'll get the same molecule. So yes, it has an axis of symmetry. That axis of symmetry is a C2 axis. It does not have a center of symmetry. It does not have a plane of symmetry, and hence it is optically active as well. So the correct answer for this question is A and D. I would like to remind all of you, and especially those who are new to these classes, that in the previous week, in the series Mirror Mirror on the Wall, we have discussed how to visualize Fisher projections. We have actually taken physical models of atoms and try to play with them. My assignments to you guys were to play with the models of the atom. So in case you've done that, you will easily be able to visualize what's going on with the Fisher projections over here. Sarthak is saying that it's very easy. That's awesome. Okay. Saksham, thank you, man. Great. It's a good question. And do you know that this is a previous year JEE advanced question? This is a previous year JEE advanced question. So in case you guys have just started your 12th class and if you've just started studying this chapter for the very first time, I can see in the chat box that you found this question easy. Congratulations, you've just successfully solved a JEE previous year advanced question as a laughing matter. Okay? There is no center of symmetry in this particular molecule. You can investigate as much as you want in order to check that out. Abhijit, dekho, if this compound is optically active, it implies there is no plane of symmetry, no center of symmetry. If there is no plane of symmetry, no center of symmetry, it implies compound is optically active. These things go hand in hand. So, agar option A correct hai, option B, C correct ho hi nahi sakte. Okay? Okay? And for ideas of center of symmetry, you can go back to the previous class and try to understand exactly what a center of symmetry is. Okay? Fine? चलो आगे बढ़ते हैं अब. ये क्वेश्चन कर ही लिया अपन ने, वो फिर से आ गया यहाँ पे. अच्छा चलो, now this question is a homework for you guys, and in case you watched Epic GOC, you would know this already. After this homework, I'll teach some definitions etc. to you guys. You have to first of all find the most stable conformation of this guy. Okay, find the most stable conformation of the given structure. Okay, first वो करना है आपको. So you know what stable conformations of cyclohexane are, right? You have axial positions, you have equatorial positions. Fine. Remember, this is my axial position, this is my equatorial position. So you have to decide in the chair form of cyclohexane where would this oxygen and where would this fluorine go. Okay. And the second thing that you have to decide is this compound optically active? Is this conformation? Okay, is this conformation optically active? Fine. So these are the two questions that you have to do as your homework. In the next class, which we will have on Wednesday, we will start from this particular idea. Right now the class is not over. We still have another 15-20 minutes to go, and we'll discuss a few more ideas that we've not touched upon, a few more interesting questions as well. But ye abhi ke liye, please make sure you take this as a homework. Tanveer is saying your lectures are awesome. Thank you, Tanveer. High five. Gautam is giving a very good idea in the chat box. Gautam, you're absolutely correct. Sarthak is saying, so previous years look so easy. It is. Previous years are easy, my friend. It's just that people don't study. पढ़ेंगे नहीं तो मुश्किल ही लगेगा. Tala Nitin, thank you so much, man. Saksham, my full name is Pahul Preet Singh Gulati. Okay, awesome, cool, nice, great. Vijay, if you have to give NEET next year, you have a lot of time. अच्छे से करो, आराम से करो. चलो जी. So, in case anyone is unclear about the conformations of cyclohexane, then epic GOC देख लेना. चलो, जब तक मैं organic करवा रहा हूँ ना, till the time I'm studying organic with you guys, epic GOC is going to be a point of highlight for all of us. चलो जी. Now, even though we have learnt all the basics of this chapter, even though we know what optically activity is, and even though we are able to solve previous year questions now, the fun thing is that we still haven't studied the definitions of what are enantiomers, mesocompounds, diastereomers, etc. And I was getting a lot of messages as to what these are. So fatafat se quickly in the next 5 minutes, let's try to understand what these things are. First of all, enantiomers. What are enantiomers? Stereoisomers which are non-superimposable mirror images of each other are called enantiomers. Everyone knows what enantiomers are, right? This is one isomer, this is the other isomer, both mirror images, both can't superimpose. These two are called enantiomers. Yeah, like if you are along with your siblings, people will call you, these are siblings. Pathetic example, but yeah, I hope you understand. Yeah, if you and your sister are going together in the market, if you don't have a sister, imagine one, then people will say that, okay, these two are siblings. These two structures on the screen are enantiomers. Enantiomers have same physical and chemical properties, however, their reactivity towards chiral agents is different. Okay? They will look the same, they will have the same melting point, boiling point, most of the times. Some of the enantiomers have different melting boiling points because of some hydrogen bonding considerations, very complicated cases. But 99.99% these have the same physical and chemical properties, but when they react with chiral reagents, okay, when an optically active compound reacts with another optically active compound, these two will react in a different manner. The enantiomers will react in a little different manner. I'll give you an example later in today's class if we have time. Okay, so enantiomers, I hope you've written it down. If you haven't, then please pause the lecture and write it down. Next, mesocompounds. We just saw mesocompounds. Yeah, I gave you an example of a mesocompound today in the class already. So compounds that have more than one chiral center but still have a plane of symmetry, okay, or I would say internal symmetry. ठीक है? So mesocompounds में ना एक statement use होती है. Okay, I'll just write that statement and I'll explain it to you. Mesocompounds are optically active because of internal compensation of rotation. For meso compounds, this is a statement that is always true. Optically, अरे क्या लिख दिया मैंने यहाँ पे? Hold on, people. Optically, अरे भैया, हाँ, optically inactive because of internal compensation of rotation. This is something that they might ask you in multiple choice questions as well. What are the correct statements? This might be one of the statements. What is this internal compensation of rotation? See, do you realize that in this particular structure, if I divide this into two halves, the top half is optically active, so is the bottom half. So imagine that when light strikes this structure, the top half rotates the light in the right hand side direction clockwise by, let's say, 10 degrees. The bottom part, since it is symmetric, right opposite to it, it will rotate the light in left hand side anti-clockwise direction by 10 degrees. So internally itself, the rotation is compensated. One half of the molecule rotates it towards one side, the other half of the molecule rotates it towards the other side. Internal compensation of rotation causes these meso compounds to become optically inactive. As simple as that. ठीक है, you could put RS configuration over here as well in case you want to do that. I mean, totally your wish. ठीक है, करना है तो कर लो. Meso compounds. Fine, noise, awesome. चलो जी. And then some people asked me, sir, what are diastereomers? What are diastereomers? Stereoisomers. Okay, mind the word stereoisomers, not optical isomers, stereoisomers. Okay, stereoisomer is a broader category of optical isomerism. Yeah. So stereoisomers which are not mirror images of each other are called diastereomers. Do you realize that the two compounds that we've made at the bottom, the left compound is a meso compound, okay, and the right hand side compound is an optically active compound? Till now, I am sure these ideas are clear to you that the left compound is meso and right is optically active. These two are stereoisomers of each other. Do you remember what stereoisomerism is? I am sure you've studied it in 11th class. Stereoisomerism, there are three categories. One is geometrical isomerism, one is optical isomerism, and the last one is conformers. Stereoisomers differ from each other in terms of the orientation of their groups in space. Position isomers are something where positions are different, yeah, structural isomers. Over there, positions are different. In stereoisomers, the arrangement of atoms in space is different. And that's what's happening over here. Meso compound, optically inactive, optically active compound, both of them are isomers of each other, but they are not mirror images of each other. Hence, these two are diastereomers of each other. Fine. These two are diastereomers of each other. एक और example दूं. One example that a lot of people do incorrectly because of conceptual error. This is trans, this is cis. Butene, trans butene and cis butene. I hope you remember these two structures. One is trans, one is cis. My dear friends, how are they related to each other? Both of these are geometrical isomers of each other. Yes, both of these are geometrical isomers of each other. But geometrical isomers are also stereoisomers. Isn't it? Geometrical isomerism is a category of stereoisomerism. So, my dear friends, these two can also be called diastereomers. Okay, these two can also be called diastereomers because geometrical isomerism is just a subcategory of stereoisomerism. Just a conceptual idea. JEE Advanced might ask you questions on this. They'll give you two structures and they'll ask you what is true about these structures. In the options, might say optically active, enantiomers, diastereomers, same compounds, etc., etc. And such a question we'll do in the upcoming class as well. ठीक है. So diastereomers, simple सा फंडा है. Stereoisomers, which are not mirror images of each other, as simple as that. Cool. Diastereomers. Then one more idea. Racemic mixture. What is a racemic mixture? See, do you realize that whenever we'll have compounds in the laboratory, they'll be in some solution, like solution bana hua compounds ka. If you've done reactions in the chemistry lab, you will realize that whenever we synthesize some compound, it gets synthesized in that round bottom flask, yeah, or in this conical flask. That is where all the compounds are. All the compounds in the laboratory are worked upon as solutions. Now, my dear friends, do you realize that there could be a 50-50 solution, which means 50% versus 50%, 50-50 solution of enantiomers? This is possible, right? Yeah, let's take a very simple case of enantiomers over here. Let's draw it from our mind. Okay, ये वाला बनाते हैं कुछ ऐसा. Okay, and the mirror image of it. Let's just put some random atoms on this. Yeah, both of these are mirror images of each other. Both of these are enantiomers of each other. Yeah, assume, okay, I hope you remember that dextrorotation and levorotation, rotating light in clockwise direction or rotating light in anti-clockwise direction, it is an experimental idea. Over here we can't do an experiment right now, so let's assume that the left hand side enantiomer, this guy rotates the light in, okay, the one that we've drawn on the left hand side of paper, let's say it rotates light in the clockwise direction by 20 degrees. Do you realize the right hand side one, the other enantiomer, will rotate light in the opposite direction in the same manner? If in a mixture I have half of the first one and half of the second one, if there is a 50-50 solution of enantiomers, do you realize that this entire solution will be optically inactive? Overall solution is optically inactive. Isn't it? Because in that solution there are two enantiomers, both mirror images of each other. One is rotating light in this direction, the other is rotating light in this direction. Overall rotation, 0. So my dear friends, racemic mixture is a 50-50 solution of enantiomers, and a perfect racemic mixture is optically inactive. Okay? If in a reaction you are creating a racemic mixture, if you put it in a polarimeter, it won't rotate light in any direction. Racemic mixtures are optically inactive. Okay? Now this was the idea of a perfect racemic mixture. But do you realize in chemistry perfection is not that easy to attain? So what generally happens is that there is always an excess of one of the enantiomers. Okay? There is always an excess of one of the enantiomers. So in reality, what can happen is, in reality, there could be a 60-40 mixture. There could be a 70-30 mixture of both of the enantiomers. Okay, so one of the enantiomers is generally in excess, and we call it enantiomeric excess. If one of the enantiomers is in excess than the other isomer in a solution, we call it enantiomeric excess. So now, to elaborate the idea of enantiomeric excess, let's straight away dive into a question. Okay, the best way for a bird to learn how to fly is push that bird away from a cliff. You've seen that in cartoons, right? The mama bird will just push the baby bird, and the baby bird will inadvertently learn how to fly. So that's what we'll do right now. We'll just take an example and we'll learn what is going on. Let's read the question. Let the specific rotation of an enantiomeric mixture be 9.72 degrees in the clockwise direction. Plus bole to plus means clockwise. Okay, and that of the pure enantiomer, if there was only the pure enantiomer, that rotation would be plus 13.5 degrees. You have to talk about the optical purity of the enantiomeric mixture. Oh, very interesting question. सोचो कैसे करेंगे? How would we do this question? This is a very nice question. Ujjwal, we'll talk about those in the next class. ठीक है? तो जो अपना Wednesday को class होगा ना, the next episode of Mirror Mirror on the Wall, we'll talk about that there. MA Partidar, see, meso compounds need to have symmetry. So for symmetry, obviously they need to have an even number of chiral centers. तभी तो हाफ हाफ हो पाएगा ना. ठीक है. सो यहाँ क्या करेंगे दोस्तों? Venkat Sriram is asking what's the difference between diastereomers and enantiomers. Diastereomers are not mirror images of each other. Enantiomers are mirror images of each other. Okay. Jeet, I've already explained internal compensation in the page of diastereomers. The idea is that internally itself, the rotation is being compensated because one half of the molecule is rotating light in one direction, the other half of the molecule is rotating light in the other direction. ठीक है? तो ये बताओ. अब Shai is asking, is this class necessary for 2020? It's your choice, man. I mean, I'd not recommend it because you might be wasting your time studying everything from scratch. Chalo, let the specific rotation of an enantiomeric mixture be plus 9.72%. So हो क्या रहा है ना, that over here there is this dextrorotatory enantiomer and levorotatory enantiomer. ठीक है? Now do you realize that dextrorotatory is the major component over here? Why so? Because overall it is rotating light in the positive direction, in the clockwise direction, in the dextro direction. Yeah. So dextrorotatory isomer over here is the major component in this particular mixture. Okay. Now the information given is if only D isomer was present, if only the dextrorotatory enantiomer was present, okay, the light would rotate by plus 13.5 degrees. But now it is rotating only at 9.72 degrees. तो अब क्या करें? People tell me 9.72 into x is equal to 13.5. Do this, okay? 9.72 into x, or let's say x percent, okay? Can you calculate the value of x over here? Hold up, उल्टा लिख दिया मैंने. 13.5 into x percentage is equal to 9.72. Okay. So overall rotation, if it was pure, would be 13.5, but only a percentage of that rotation is happening. Can you tell me what is this value of the percentage over here? Siddharth, just read the title, bro. People, can you give me the percentage over here? X calculate कर सकते हो? 13.5 into x by 100 is equal to 9.72. करो करो करो, इससे आइडिया आ जाएगा. Prithvish is saying it is 72%. Okay. Rakesh is saying it is 72%. Savi is also saying 72%. So you guys are saying that x is equal to 72%. Is that what you're saying? So my dear friends, what this implies is that 72% excess exists for the D isomer. Am I right? 72% excess exists for the D isomer because the rest of it is getting compensated, है ना? So 72% exists for the D isomer. Apart from 72%, how much is there? So 72% is just D isomer. The remaining 28%, yeah, 100 minus 72, 28 ही आता ना, yeah. So the remaining 28% is a perfect racemic mixture. Okay. If it was pure, 13.5. Not pure, only 72% of that, 9.72. So 72% is just D-isomer and 28% is perfect racemic mixture. What does perfect racemic mixture mean? This implies that there is 14% D and 14% L. Right? So can you tell me what is the final composition of this mixture? What is the final composition of this mixture? Final composition is 72 plus 14. कितना बना? 86% D and 14% L. चमकी बात? Did you understand what went over here? If only D was percent, rotation would have been 13.5, but only 72% of that rotation is happening, which means that 72% is the enantiomeric excess. 72% excess of the D isomer exists apart from the racemic mixture. So how much is the racemic mixture? 14% and 14%. So total amount of the D isomer is 86% and total amount of L isomer is 14%. My dear friends, watch this part of the class again if you have any doubts with it. In the upcoming class, we will discuss more questions of that sort. We will discuss about questions where there is chirality without a chiral center. And before I leave you guys now, because I have to take another live session at 8, this is something that you can refer to in case you want to be a regular student with us. Then the links are given over here, vdnt.in/ytjee21 and YT NEET 21 for NEET examinations. And in case you want to crack your examination in 2022, then these are the links. These are full courses which we are giving for free because of the lockdown. Oh ho, maza aa gaya. Yeah, fine. So I'll leave you guys right now. Thank you so much for joining in. It was a nice fast-paced session. In case you want to watch it again, you're free to do so. If you have any doubts and queries remaining that I couldn't answer in the chat box, sorry for that. Please leave them in the comment section down below. And the next episode of Mirror Mirror on the Wall airs on Wednesday. It might be the last episode depending on our speed. So please be prepared with all the basics, all the ideas, because on Wednesday we are going to discuss supremely advanced concepts. Fine. Chalo. Thank you so much for joining in, people. Bye bye. Take care. See you soon.